bacteria do a lot of beneficial stuff for us that we're just beginning to understand. And when you perturb the native composition of a healthy human microbiota, that's what it's called, this can manifest in all sorts of different diseases, right? So there are like changes in your microbiome associated with like neuropsychiatric disorders and all this sort of stuff that we're just beginning to understand a little.
Hi, everyone. Welcome to episode 6 of the Public Principle. Here today with Jon Stokes. We met maybe a couple of years ago.
Yeah, you're
uh,
something like that.
I have a lot of admiration for what you're doing, and I'm actually glad to have you here today. And we'll chat a little bit about your work and all sorts of cool stuff related to AI for
Yeah.
drug discovery. So, why don't we begin with a little bit of an intro about yourself? I'd love to hear a little bit about you and what you're working on right now for the audience, please.
Yeah, so I'm not an AI guy. I'm probably the least AI guy you're ever gonna talk to here. You know what I mean? Like, I'm a microbiologist. I cut my teeth pipetting E. coli all day. Um, so it's kind of funny, like, we can go way back. I was born in the hospital that my building's attached to.
Oh,
You know what I mean? Like,
uh,
I didn't end up going very far. I did my undergrad here at McMaster. I PhD here at McMaster. My PhD was focused on like small molecule chemical screening uh, for molecules that elicited interesting phenotypes in bacteria, right? Of course, with the slant of discovering new antibiotics. So that's like what I'm trained to do. You know what I mean? Just like pipette molecules and bacteria all day. Um, but when I finished my PhD, I moved to Boston to do a postdoc. And I was in Boston, and this is one of these interesting stories. It's like you by accident find yourself in a room with people who you shouldn't have been next to, and then you end up doing stuff that like you never intended to do. You know what I mean?
mm-hmm. Yep.
So, I was a postdoc in Boston, and I was being supervised by Jim Collins, and I was in some meeting, and it was some folks from the Collins lab and some folks from Regina Barzilai's lab. So Regina Barzilai, yeah, there you go. Computer scientist at MIT. Just like so rad, man. I love her to death. Um, and we were all chatting, like Jim's crew, Regina's crew, and it was like, how can we do something, anything like potentially maybe interesting, or at least not useless, at the intersection of like something related to antibiotics and something related to ML, right? And it's this meeting and everybody's talking blah blah blah. But partway through, we came kind of to this realization, like coming from my background where all I did was chemical screening, like there is a world in which we can leverage, you know, antibiotic screening data to train some of her molecular property prediction models, and maybe something will work, right? And so that was sort of our first attempt, right, into leveraging ML for antibiotic discovery, as we've come to be doing it over the past, whatever, 6 years now or whatever it's been. Um, so yeah, it's like I found myself, at this interesting intersection between ML and drug discovery because I was like in a meeting that I shouldn't have been in, you know, some like random Tuesday afternoon or whatever it was. Um, and then I came back to Mac. This was I've been a faculty member here for about 3.5 years now, and my lab just works like kind of squarely at this intersection now. Like half my crew are computer scientists, the other half are wet lab experimentalists, and we're developing ML models and applying them for new drug discovery applications with a specific focus on novel antibiotic discovery. Right. We have some other stuff that we're doing, but we spend most of our time thinking about, how do we make antibiotics fast and cheap?
Um, which, yeah, I mean, it's a little bit tongue in cheek, right? But of course, I think it's really, really important. And, you listen to some other people, this one of those, I don't know, big challenges of humanity, right? Like we haven't discovered a lot of new antibiotics for many years, maybe decades, right? And,
Yeah.
at some point, well, I mean, like a few years ago, we all kind of, went through this pandemic, right? That, turned out to be a little bit more important than we could imagine. So, um, do you think I mean, I don't know. Was that something that took part in your motivation to work on this stuff? The fact that it's important at the society level, or was it like, you know, let's just just stumble upon?
Dude, so me ending up in microbiology was just like another accident. Like a pure so I can tell you that story too, it's funny. Um, so this is gonna get weird a little bit, and then I'm gonna bring it back. Do you trust me?
Yeah, did not a good episode.
Alright. So, um, in h like, high school and early undergrad, I grew up in a neighborhood, near the previous dean of the Faculty of Health Sciences here at McMaster, and I was just like this, like, dink little kid running around town, like, causing trouble, just whatever, and, this guy, just, you know, a saint, a guy named John Kelton, comes up to me one day, he's like, "Hey, do you wanna work, and, like, do gardening and cut my grass and stuff?" And I was like, "Yeah, sure do, whatever." And I ended up, doing his yard work as, like, a high school student and into undergrad. And between my last year of high school and my first year of undergrad, he said, "Do you want to work in my laboratory over the summer?"
Huh.
He's, like, a world-renowned hematologist, like genuine, like, leader in his field. I didn't know that at the time. I didn't, like and if if I heard that before, I didn't appreciate it, so I was just like, "Yeah, this'll be fun, whatever, let's see."
Yeah.
And I fell in love with laboratory research, as, like, a teenager, right? Um, and I spent a few years in his lab during undergrad, and it was time for me to find a 4th year thesis, right? A 4th year undergraduate thesis.
Mhm.
And I say, "Hey, John, like, I'm looking to do something potentially a little bit different. What do you suggest?" He said, "You gotta go talk to a guy named Eric Brown." Eric Brown at the time was the chair of the Department of Biochemistry, and it just so happened to be that he was another world expert, in microbiology. Like, he's a chemical biologist, an antimicrobial chemical biologist. So I cold email Eric, right? I'm just like, "Hey, my name's John. I'm currently working in John Kelton's lab as like as a student. I'm looking to do a thesis. Can I join your lab?" Totally just like the simplest nothing email ever. Should have been deleted. But for some reason, Eric was like, "Yeah, let's have a quick chat, yada yada." Long story short, I ended up doing a thesis in his lab, right? I remember when I started, I didn't know what bacteria were. I didn't really know what antibiotic resistance was. I knew what antibiotics were kinda, but like I didn't know anything. And I'll never forget this. I started in September. This would have been September of 2010 as an undergraduate student in his lab. By October of 2010, I knew I wanted to do a PhD in his lab. And it's not because I had a, like, deep comprehension of the work or the significance of the work, but it was a lab that I liked going to work in every day. The simple question that I asked myself was, "Could I see myself coming here day in, day out for, like, 5 years and probably still have a good time at the end of it?" And the answer was overwhelmingly, like, yes. And it was just because, like, the culture of his lab was awesome. The people in his lab were incredible. They were hardworking, dedicated, fun. Um, and that's that. Like, that's how I found myself, studying AMR and like, eventually falling in love with this topic, right?
Yeah.
There wasn't some, like, plan behind it. It just happened, much like me, just happening to find my way into ML by accident. You know what I mean?
Yep.
Um, but you're totally right, in what you were saying earlier, right? It's like, this is like a legitimate issue, So I'm trying, like, rough numbers, right? So you were saying, yeah, and you were right when you said it a couple minutes ago. Our last antibiotic that's like truly novel, structurally and functionally, was discovered in 1987, right?
Wow.
So we're going on what's that, 40 years almost,
Uh,
right?
yeah, yeah. I was born in the 80s, so it's kind of funny to think of the 80s as like, so long ago. But
I
yes.
know. And you know, and there are like the economic incentives, let's say, the financial incentives to, like, make new antibiotics just isn't there right now.
Yeah, so that's an important topic. Let me hold on to that, but I'll share a an interesting stat. I was A while back, I was playing with Claude, which is actually my favorite um, LLM. I don't get paid to do that, so I just happen to like how Claude.
Not not a paid promotion.
Not a paid promotion. But I was asking it, well, let's run through the entirety of human or Homo sapiens history, 3 million years ago, and try to figure out, what are the causes of death? Like,
Man,
why did people die? Did they die of malnutrition? Did they die of something else? And of course, the main cause of death throughout human history was infectious disease, right? But most people, I would say throughout human history died of infectious disease. A few people died of aging, right? A few people died of other things, war and malnutrition and other things. Uh, and then of course, humanity discovered antibiotics and then we stopped dying of infectious disease. And people today just don't realize how transformational that was, right? Like people could go and die, in their 20s and 30s and 40s, and that was perfectly normal because, you're, walking around, doing your things, some animal bites you, and there you go, you're done, right? And now we don't. And we just don't appreciate, how good we had it today.
I know, it's like, yeah, our ability to control infection bought us an extra probably 30 years of health span, right?
Yep.
And now, yeah, we have the luxury, if you wanna call it that, of, getting sick and dying from diseases associated with, like, old age, right?
Hmm. Hmm.
Um, and yeah, it's like antibiotics. Well, so I teach an undergraduate course here, and it's about antibiotics. It's kinda like half about antibiotics and then half about AI, but like, I sneak the AI in kinda, like, gradually. Um, but one thing I teach is, like, antibiotics are not, like, sexy, right? It's not cancer or, like, neurodegeneration or whatever. It's like, yeah, antibiotics. It's like like, they kill bacteria, and then we can, like, actually do other stuff. So and it's like, there's something, like, simple about that, but again, it's, like, not I don't know, like, not, like, super, like, there's no wow factor necessarily. Um But to me, that's almost like why I like to be in this space, it's like they're just essential medicines that we need to have for the rest of medicine to work. You know what I mean?
Yep.
Like, we always think about, like you said, it's like, we're playing outside, we run through a garden, we get our legs scraped up, and we die from an infection, right? That's what people think about. Um, and which is, I mean, it can be true, right? Like this year, 1.5 million people are gonna die from a drug-resistant infection. And if you do the math, that's one person about every 20 seconds, right? Day and night, all year. Um, but that's like part of what antibiotics do, like, or save lives. But another part of what they do is they enable modern medicine to be modern. So there's a ton of medical procedures, things like, preterm births, immunosuppressive cancer chemotherapy, anything invasive like surgery or joint replacements, whatever. All of these procedures can only be safely and routinely practiced because of our ability to treat or prevent infections that will inevitably arise. If we run into, if they're like a world that could exist in which we can't reliably control infection, all of these modern medical procedures become too risky
Yeah.
to justify,
You couldn't
right?
do any surgery, right?
I mean,
People are going to get infected as you cut them.
like the picture I like to paint, think about this. It's like in 20 years, you know, you get arthritis, you need a new knee.
Mhm.
Like, the technology exists, you could get your new knee, but the probability of you getting an infection that is untreatable is so high that the risk of having that knee outweighs the benefits. So instead of you getting a new knee, your surgeon wheels you out a wheelchair, right? And saying like, "You're gonna have to be with this right now." So it's
Mhm.
like these are like quality of life medicines, you know what I mean?
Yep.
And that's something, that's often not, strongly considered, I would say.
No, 100%. Um, Let me work back a little bit, for the benefit of people that don't come from the biology world,
Yeah, yeah.
haven't spent much time with this. So, like, what is an antibiotic versus what is an antiviral versus why is an antifungal? Like, why are those things different? Microorganisms, right? Like, come in different types. Like, why do we need all these different molecules for different things?
Yes, super good question. So, bacteria are like they're single cell organisms that don't have like bacteria were the first probably things that lived on our planet. Like whatever, 3 point whatever billion years ago. They were the first things to kind of pop up. Um, and they're super, super small, right? They're about a micron in size. They don't have membrane enclosed organelles. They're just like a membrane sac filled with DNA and proteins and stuff, right? That isn't technically true, but it's true enough for now, right? And they come in, like tons of phylogenetic diversity. There's a ton of them. They live naturally, like in and on us. So we humans, any human you talk to is roughly equal parts bacteria and human, right? Like we have trillions, roughly like 1 to 1 of bacteria living in our gut, on our skin, wherever, that all are, contributing to our overall human health in some way. And then there are
Soundbite. I'm cutting that out and putting it on YouTube, right? Like we have, I think, the same amount of bacteria on us that we have human cells, right? Something like that.
yeah, we're equal parts bacteria and human.
Mhm.
Um, and what's super and bacteria do a lot of beneficial stuff for us that we're just beginning to understand. So like in humans, we have a microbiome. Like that's the composition of bacteria that live in our gut. Like they do tons of beneficial stuff that we're just beginning to understand. And when you perturb the native composition of a healthy human microbiota, that's what it's called, this can manifest in all sorts of different diseases, right? So there are like changes in your microbiome associated with like neuropsychiatric disorders and all this
Mhm.
sort of stuff that we're just beginning to understand a little, right? But then there are all these other bacteria, and oftentimes they live in and on us too. But they can also make us sick. They're pathogenic, right? A really common one, a foodborne pathogen, I'm sure we've all heard of is E. coli, right? E. coli is a bacterium that is often associated with like, foodborne illnesses. And you eat it and then you get like diarrheal infections and you feel like shit and all this stuff.
Mhm.
And then another super common one that I'm sure everybody's heard of is Staph aureus. MRSA is the one that's often touted. Methicillin resistant Staph aureus. This is a really bad like skin infection. Like if you go to a gym, right? And you like
Mhm.
scrape up your leg on a mat or whatever,
Yeah.
and you get infected, that's often a staph infection. Right? Um, so yeah, these are all like single cell like microbes. And when they make us sick, we have to take antibiotics. And these are molecules that are, for lack of a better word, bacterial poison. Like these are molecules that kill bacteria specifically and don't kill us while they're killing the bacteria. Um, And I mean, we really briefly touched on this earlier. We've only had antibiotics for the past less than 100 years, right? Like our first modern antibiotic, if you want to call it that, was discovered in 1928 by Alexander Fleming. Do you know the story behind this? Or like the supposed like anecdote?
I don't think I have. I mean, I guess it was something like he had some fungus growing on in his lab and
Yeah.
something like that, but I can't really remember. So, but yeah, if you wanna.
So here's the story. I don't know whether this is true, but I read it somewhere and it sounded cool. And I was like, I'm just going to keep saying this. So, um, what I read was Alexander Fleming, so he was a microbiologist, and his lab was kinda messy. Like, he wasn't, like, everything had to be where it had to be. His lab was a lab, there was stuff everywhere. And it was, like, the August or something of 1928, and he said, "I'm going on vacation, I'm tired." He goes on vacation, and he had a plate of Staph aureus, remember we were just talking about it, in a petri dish sitting open in his lab, just on a bench. Goes on vacation. 3 weeks later, he comes back. On that plate, there's a whole bunch of staph growing, but then on one edge of the plate, there's something else, just like this fungusy gross stuff. But around the fungusy gross stuff, there's an area where all of the staph had been killed off, right? So he looks at this plate and he goes, "That's super weird. Why is this happening? What is this gross fungusy thing? And what is it making to make all my staph die?" Right? Turns out that the gross fungusy thing was a mold called penicillium, and it was making penicillin, which is one of our like and our first novel, like first modern antibiotic, right? And since that discovery in 1928, and it's like clinical implementation soon thereafter, I've seen hypotheses like penicillin has maybe saved somewhere between like 300 million and 500 million lives or something, right? it, like, arguably the most consequential discovery in medical history, and it was made by a combination of an accident and just someone who saw an interesting thing and said, like, "What's cooking here?" You know what I mean? Like, it's just, like, the coolest story ever. And that idea, right, of, like, him looking at mold on a plate and it killed staph, and that's useful clinically for, like, human longevity. Like, people took that idea and ran with it. So most of our antibiotics that we currently use in the clinic, right, to treat bacterial infections in people were discovered between the 1940s and the 1960s, eh? Like, these are not new molecules, like, these are old molecules, and what's really cool is the overwhelming majority were not synthesized by chemists in a laboratory. They were discovered by looking for other bacteria that live in dirt and asking which of these bacteria are making antibiotics, right?
Yeah.
And then we just take those antibiotics that are made by other bacteria living in dirt, so-called natural products, because they come from nature. We purify them, see if they work, and then if they worked, we started giving them to people to treat infection, right? Like, that's the history of antibiotics. It was largely like digging up molecules that were produced by soil-dwelling microbes and then repurposing those molecules to treat humans.
Yep. Which is it's quite amazing. I think, well, for me, right, like, I'm an engineer, right, and I look at how much we have learned about biology and structural biology, and I think, well, surely with all our knowledge of structural biology, most of the new medicines come from looking at protein structures, and that is very, very far from true, right? Like, so much of it just comes from, like, doing things the old way. Just get a chemical, you put it in a petri dish and see what happens.
Dude, that's what's so cool about antibiotics. So, I'll give you a brief history. So, that period of time that I just talked about from the 40s to the 60s, that's called the golden era of antibiotic discovery. Like, the vast majority of our clinically used antibiotic classes were discovered then. What happened though, come like the middle of the 60s to the early 70s, somewhere in there, is we kept discovering the same antibiotics over and over again through this approach by looking for microbes that live in dirt that were producing antibiotics, right? Through that same sort of, that's called natural product mining. We kept finding the same things over and over again. And we were like, well, this is annoying. We're not finding anything new. So we turned to other approaches to try to find new antibiotics. One was high throughput screening of synthetic chemical libraries, right? So this happened, I like started kind of like the 80s in there. And a couple things happened in parallel. So like recombinant DNA became a thing. You could like clone a gene,
Yeah.
right? Two, we started to amass these like largish scale synthetic chemical libraries that could be tested systematically. And the third thing that happened was laboratory automation started to become a thing, right? Like the early eras of laboratory robotics. So that opened up a really interesting approach. And the idea was, well, if we can determine which genes in pathogenic bacteria are essential, meaning if we try to delete them, that cell dies, right?
Mhm.
Or the cell technically is non-viable, right? Well, if we could find a molecule that just inhibited that protein, right? That cell would also die, right?
Yeah.
Because it's the same as deleting the gene,
Makes
right?
sense.
So what happened is, a whole bunch of folks were identifying essential targets, right? Purifying the proteins, testing chemicals against all of those essential proteins, and then saying, here was the hypothesis. If I have a molecule that's super potent at inhibiting some essential bacterial protein, that will be a good starting point to make a novel antibiotic that I can give to people.
Mhm.
So that was done for 30 years or something. Do you know how many novel antibiotics were discovered through so-called target-based antibacterial screening?
I suspect the answer is going to be a small number.
Yes, it's very small. It's 0. None.
Why? But why? What is the reason for that? Like, what is the intrinsic complication with that approach? Because intellectually it makes so much sense.
The logic is super clear, right? Here's what empirically what was happening. We were ending up with molecules that were incredibly potent inhibitors of enzymes in vitro. So, how these experiments work is you have like a test tube filled with purified enzyme that's doing some function, some biochemical function that you can monitor, right? It's turning over a substrate or whatever. You add your molecule. I don't see any substrate turnover anymore. I have a good inhibitor. And what was happening is we were finding these molecules that were really, really good enzyme inhibitors. As soon as we took that same molecule and tried to use it to kill a bacterium in a dish, it didn't work. It did nothing. And that's because sometimes for, one type of bacteria, actually for multiple types of bacteria, those molecules had a difficult time actually getting into the cell,
Mhm.
right? So you have, let's say this is the inside of a cell down here. Here's your target. My molecules are out here. They need to get through here in order to get to my target.
Yeah.
The molecules weren't able to get into the cell to begin with to engage their target, right? Um, so by trying to identify molecules using these like super simplistic experimental systems, right? Purified proteins in a test tube, you're kind of negating the biological complexity, right?
Yep.
And fundamentally, and I know you appreciate this, like drug discovery is like fundamentally a multi-property optimization task, right? But like because think about it, like you have a single molecule, and let's stay with about antibiotics for a sec. You have a single molecule that you need to have activity against whole bacteria, meaning they have to get inside of the bacterium, bind to their biochemical target, and they also have to be soluble, and they also have to be, bioavailable. They have to have good pharmacokinetic and pharmacodynamic properties. They can't be overly toxic. They have to be, excreted. Like there's all of these properties that all have to line up in a single structure in order for something to be, a candidate medicine. You know what I mean? And I think by taking these hyper reductionist approaches, that were, rational, but, you know, failed,
Mhm.
you're not considering sufficient biological complexity at the onset.
Yep.
So you ended up with like nanomolar inhibitors of enzymes that didn't do anything in like more sophisticated biological systems. And when I say more sophisticated biological systems, that says like I'm growing bacteria in a test tube and it doesn't kill them anymore. You know what I mean?
Yep. But I think one of the really interesting things um about this is that you don't have to use those simplistic models, right? So like um if you're just let me rephrase that, right? There's a long road between finding a good binder for a protein target and actually finding, something that has the therapeutic effect that you want, right? But in bacteria, you could apply it directly to the model. You can get that bacteria in culture and then, put the, molecule in there and then test it right there, right? Like with other diseases, you can't really do that, right? Like, you can't,
Exactly.
really do that with, some neurodegenerative, disease, right? Like it's a lot harder to do, but with bacteria, you can't, right? So like, how is that approach, uh, you know, I imagine that approach is a lot better, right? I mean, maybe like, we've seen or you've seen more success doing that,
Yeah.
right?
100% do. What you just described, so what I described that didn't work was target-based screening, right?
Mhm.
What you just described was phenotypic screening. You're chasing a phenotype of a cell. And remember I said all of our antibiotics or the most majority of them were discovered like before 1960
Yeah.
or like the mid 1960s. All of those were discovered through phenotypic screening, right? And here's how the approach worked. Someone would go get a shovel, dig up some dirt, grow the bacteria that were living in that pile of dirt, extract all the metabolites out of those bacteria, and ask, are there antibacterial molecules in this extract? Right? And how they would test that is they would have their pathogen of interest, E. coli, staph, whatever it was, and they would say, in this like, you know, dirt bacteria juice, can I kill my pathogen? And if the answer was yes, okay, there's an antibiotic in here and I just have to go dig it out. That's how it worked. And like like antibiotic discovery started slowing down when we tried to get fancy with it, right? Oh, I have this new protein. I think like it's essential. I can't delete the gene. This is going to be a perfect target, and then, nature had other ideas. You know what I mean?
Yeah.
But phenotypic screening is now becoming, like cool again, right? Because it works. It just the probability of success if you're doing phenotypic screening, in my opinion, is way higher than if you're doing, a quote unquote rational target based screen, right?
Mhm. Um, it also kind of combines really well with AI methods, right? Like, one interesting thing that you see, when people build software or build AI models is that you need some way of testing what you're doing and get some feedback on it, right? And the faster your iteration cycle is, the better. I think this is a universal truth across all of software development, right? Like, if you build an app and it takes 5 years, to go and get some feedback, and then every time you iterate back and forth, you
Yeah.
need to do that. Then the progress is going to be very, very slow, right? And one of the cool things, maybe why we have seen this super fast progress in AI in recent years, is that you can train a model, get some predictions, evaluate whether it works or not, with using good standard benchmarks, and then iterating back and forth. And then you do that, day in and day out, multiple times a day, right? And
Yeah.
then you get, much, 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 much faster progress, right? So I think a cool thing in, I guess, antibiotic discovery versus, finding drugs for cancer, right? Is that iteration cycle can be done much, much faster.
Yeah. Yeah. And that's largely due to, just the nature of the biological system. So to put it in context, like E. coli and, other pathogens other bacterial pathogens, when we're growing them in the laboratory, they have what is called a doubling time of like 20 to 30 minutes, meaning like one cell becomes two in 20 minutes, two become 4, 8, 16, 32, and you have like this exponent. So we do experiments like whole cell bioactivity experiments in a day, right? Because cells grow so fast. Um, so by like just like because we're working in bacterial systems most of the time, yeah, this does enable, these relatively rapid iterative cycles of like model refinement, active learning, if you want to call it. The actual bottleneck in our type of work, you know, applying whatever model architecture for de novo molecular design or molecular property prediction or whatever, is the synthesis of the molecule, right? So I'll explain at a super high level how we go about this, and then you can tell me why it's stupid. So we set off with some drug discovery project. Like we want to discover a new molecule that kills. My favorite bug is Acinetobacter. Nobody cares what that is. I care what it is. So I'll tell you this. So Acinetobacter baumannii, we're gonna get nerdy just for a sec, but it's super rad actually. So most bacteria that make humans sick, like you dig it out, like they live in nature, right, in dirt and whatever.
Yep.
There's a bacterial species called Acinetobacter baumannii, and its native ecological niche is like hospitals, like doorknobs and hospital equipment and stuff. Like, it's what we call a professional pathogen. So far as we understand, it exists just to make us sick,
Oh,
right? And it's resistant to everything, and mortality is super high and blah, blah, blah. So if we want to say, okay, I want to discover a novel Acinetobacter drug, which we need, like the world genuinely needs new Acinetobacter drugs. Um, and we want to take some ML approach to it. My favorite way of going about is treating this as a phenotype task, right? I'm going to gather a training data set of a bunch of molecules that kill Acinetobacter in a dish. And I'm going to use that phenotypic screen as a training data set to train, a molecular property prediction algorithm or a molecular design algorithm, whatever. And then, you'll run a whole bunch of predictions if you're treating it as like a discriminative task, or you'll design a whole bunch of molecules if you're treating it as a generative task. And then, computation meets reality, and we say, okay, we have to make all these molecules, right? That's actually the bottleneck, right? Oftentimes it'll take us, on the order of like a few weeks to order a batch of molecules, get them into the lab, and then it'll take us literally 18 hours to test them, right?
yep, yep.
So the
Or
actual
longer, right? Like synthesizing a novel molecule may take, weeks or months, right? Or, if you can, like sometimes just,
yeah,
nobody knows how to do it.
so like using, what I'll call like typical molecular generation algorithms, yeah, like you can design molecules that are synthetically intractable, they cannot be made. Or if they can be made, it's like a 50-step synthesis with a 0.1% yield, and it's gonna cost you like 20,000 a milligram, right? Which I can't afford, right? Because 'Cause I'm not like Merck.
Mhm.
Um, but yeah, like even the type of molecules that we make with our which are all synthetically tractable, we have known reaction schemes, known molecular fragments that are used to build these molecules, etcetera. We're still waiting for a few weeks to get these in lab, right? So, the actual when if we're talking about, iterative model refinement based on real world data, our bottleneck as an academic laboratory trying to do this shit is the acquisitions of the molecules that were outputted by the model, right? Because living in bacteria land, we test them in a day, right?
Yeah.
And then we retrain the model and that takes a day. We run a new set of predictions or generations that takes a few days. And then okay, it's like now we're sitting for a few weeks to actually get these chemicals in, right?
Yep. Yep. It doesn't make a difference if you use catalogs of molecules, or like say libraries that are based on, synthons or like, smaller building blocks that may be easier to assemble or not, or like there's just those libraries do not cover enough, I guess, chemical space to be useful for it.
I actually think they do. So most of our when we go to run predictions, let's say, or do, de novo molecular design, we're working in these, combinatorial chemical spaces. So these are molecules that are made up of like predefined synthos and predefined reactions, right? Um, I actually think there is enough chemical diversity and there are like a sufficient total number of molecules in these, I'll call it like synthetically accessible spaces that novel antibiotics exist in there, right? We just have to find them, right? Um, but even so, like by the time, we sort of like curate a list of experimental candidates, source them, have them synthesized, and then get them back to the lab, we're still talking weeks, right? Because it's like,
Yeah.
honestly, I feel like if we want to be like kind of like even a bigger step back, it's like stuff has to like travel like by plane, train, and automobile and stuff, right? It's like moving stuff around the world takes time, right?
Mhm. Yep.
So it's oftentimes like that's kind of what we're waiting on. It's like, oh, cool, it's on a plane now. So now it's on a boat or whatever. I actually don't think it's on a boat ever. It's always a plane or like a car.
Yeah. But I
But
mean,
you get it,
for
right?
there are small packages, right? It wouldn't make a lot of sense to like
It
ship them by boat.
but you get it, right? It's like, like when we're working with chemical synthesis companies from wherever, you know what I mean? Like their synthetic chemistry machine might be like super duper efficient, right? But then they have to like get it to us, right?
Yeah.
And
Well, yeah, yeah. I mean, like if it comes from, from Ukraine or from China, right? And I think, still, right, like, many cases, a human needs to look at it, right? And figure out, does this, work or not, right? I think Yenamin, for example, right, which has like one of the largest catalogs, they say they have this guarantee of synthesizability, which is only like what, 80%, 90%. So sometimes they will tell you, yeah, we can make this, and then you ask them for it, and they can't.
so okay, another like here's another non like unpaid advertisement. Like we work with Edamine all the time. Like Yuri's like the man. I love that guy to bits. Um, and yeah, like honestly, like after working with them for a few years now, like when we do our molecular designs or whatever, you know, yeah, they'll have an 80% synthesizability rate. So when we go to curate molecules, we'll just add 20% more than we actually want to acquire in lab, knowing that some number will be, non-synthesizable or they'll be, you know, slightly less pure than required, all this stuff. Right. But this is stuff you just sort of like learn, as you're going through and you've run like multiple like drug design projects, whatever. You kind of see like, which points in these whole processes like need a little bit of like, leeway here and there, whatever. But it's stuff, yeah, you sort of like learn on the go. It's just as like something you don't see in a method section, right?
Yep. Um, Let me jump on a couple of things that we touched on as well, uh, which I think may be interesting for some of the people listening to this. So, um, you know, uh, a virus and a bacteria are not the
Yeah.
same thing, right? I think sometimes people that are maybe not as familiar with it, would get a flu, right? And say, well, why can't I just take antibiotics for the flu? Well, I don't know why does an antibiotic, does not work for the flu, right? And is finding antivirals, easier or harder than antibiotics? What do you think?
Yeah. So super good question. I like I'm a bacteriologist, so that's all I understand. But other common types of microbes you'll hear are fungi,
Hmm.
right? Like fungal infections, they cause like
Yeah.
lung infections all the time and stuff. And viral infections. That's like the cold or COVID, right?
Yeah.
Viruses are technically, I might make a couple people upset, but I don't think that many. Like they're not alive. Viruses are not like self-replicating organisms. For something to be considered living, it has to be able to divide independently of other stuff. Viruses are dependent on infecting a host, and then they hijack the host machinery, and that's how they make more of themselves, right? But you can't take a virus, put it in a test tube filled with food, and say divide because it can't. It doesn't have the machinery to.
Hmm.
If you take a virus and a host and put both of them in food, the virus will hijack the host and then it will be able to make a bunch more of
Hmm.
itself. And then what happens is those viruses escape the original host, go find other hosts, and then repeat the process over and over again.
Yep.
So, antiviral molecules are stuff that inhibit, essential viral machinery. Antibiotics will do nothing for a viral infection because antibacterial molecules don't have a target in viruses, right? Similarly, fungi are, probably, I don't know, a couple billion years diverged from bacteria, and fungi are much closer to human biology than they are to bacterial biology, right? So, fungi and humans and plants and all this stuff, those are called eukaryotic organisms. These are organisms that have like, organelles and like membrane enclosed organelles and like they're really complicated. Um, and similarly, like an antibiotic won't work against a fungus because fungi don't have the appropriate like biochemical machinery that antibiotics target.
Yep. Funny coincidence. I literally just started watching The Last of Us, right? Which is all about a fungal
Oh yeah, yeah,
infection
yeah.
and its control of people. And anyway, I mean, it's very well made. So highly recommended. For fiction. But I always understood that because fungal cells are so much closer to human cells, that one of the main issues over that is not so much finding poisons that kill fungus, but finding poisons that will not kill the corresponding human cell, right? So you can find, you know, famous human cells where you can find all sorts of molecules that are toxic, right? But the problem is, you can't have that thing, kill you, right? Then it's not
So
useless
like
medicine.
that's the thing, right? So like let's say, we can use bacteria and fungi as two really good examples for this. Um, we're actually working on an antifungal drug discovery project with a super good friend of mine. Her name is Rebecca Shapiro out of the University of Guelph here. Like just down the road, half an hour down the road, for where I'm sitting. She's like the coolest, like most down to earth and like smartest fungal geneticist like ever. And she's just like so rad. So shout out to Rebecca. But anyway, I actually met her. We postdoced in the same lab. We overlapped for a few months. That's
Nice.
where that's where I met her. Um, anyway, so if you have a fungal infection or a bacterial infection, here's what's happening. You have bacterial cells or fungal cells that are growing in you somewhere, right? And they're doing biological stuff to make you sick, right? That's a good enough explanation. And what we have to do then is design a pill, like a molecule that someone can eat or have injected or whatever. And that molecule will go to the site of infection, kill the bacteria or the fungus, and not kill you while it's doing it. That's like the fundamental task for like if we're like treating infection, right? And you would imagine, rightly so, as you said before, because fungi are so much closer to humans biologically, the biological space that we have to play in that differentiates fungus from human is a lot narrower than the biological space that differentiates bacteria from human, right? So I think we only have something like 4 classes of antifungal drugs, and they all kind of do similar stuff, right? And it's because the differentiating biological processes between fungi and humans are like so few, right? Antifungal drug discovery is really, really hard because we share so much biology.
Yeah.
That's like why discovering a new cancer drug is super hard because cancer is fundamentally us with a couple like little
Yeah.
weird biological things happening different. And that's why every cancer chemotherapy is super toxic,
Hmm.
right? Because sure, it's killing the cancer, but it's also killing off a bunch of normal cells too, right? Because again, the biological space we have to play with between cancer and normal is even smaller, right?
Hmm.
And this goes back to this like multi-property optimization task stuff we were talking about, right? We need molecules that do like a whole bunch of things simultaneously, and one of those things it has to do is engage with like some biochemical target in the thing we're trying to kill, and hopefully avoid binding to a whole bunch of human stuff. You know what I
Yep.
mean?
Yep. Yep. Of course. Jumping into another thing that may sound a little bit sci-fi, but like people did this a long, long time ago, right? So pages, right? Like, sometimes I guess you don't need a molecule, right? Like, back in the day, people would go and look at a virus that kills bacteria, right? And then you say, well, if the virus kills the bacteria and it doesn't kill me, can I use the virus as an antibiotic? And I think that is a pretty cool idea, right? Like, I mean, you could think about it as other ways, right? Like, instead of having a small molecule that has to satisfy all these complex properties, can you find a virus that would kill this pathogen?
Yep.
I don't know. I thought that was very sci-fi, right? But people did this, years ago.
This has been around for a while. It's just like it doesn't happen that often. Um, and I actually don't know why necessarily. So yeah, so for everybody listening, a phage or a bacteriophage are virus particles that attack bacteria, right? So we like uh what was it? SARS-CoV-2, that virus a few years ago attacked us. Bacteriophage attack bacteria specifically and don't attack human cells or other, animal cells, whatever. Um, so these are tiny little, virus particles. What they do is they recognize molecules on the cell surface of some bacterium, and generally that interaction is quite specific, right? The phage recognition of some bacteria, that's generally very specific. And then that phage will then infect that bacteria. And if it's the right kind of phage, it will cause that bacteria to explode, killing it and releasing, thousands of additional phage particles that will go bind to other bacteria and kill them all too. Um, yeah, phage therapy is a thing that is like sometimes practiced. I don't know how often. I should have looked it up. I don't know. Um, the primary issue that I've heard cited, not being like an expert in this, is frequency of resistance. Right. So what is that? Like, let's talk about antibiotics for a second, then I'm going to bring it back to phage. Every antibiotic we ever discover ever will succumb to resistance. And what does that mean? You have to think if you have a molecule, an antibacterial molecule that sticks to some, let's say, protein in bacteria, right? If, like, do you know how like evolution is a thing?
Yeah, yeah.
So
It's not.
if you have, let's say, a billion bacteria sitting in a test tube, and you take your antibiotic molecule that sticks to some protein in those cells, just by accident, some of those cells, like a couple of those like billion bacteria, will have made a mistake when copying their DNA and that will have introduced a mutation in your protein of interest, like the protein that antibiotic is supposed to bind to, such that it won't bind anymore, right? It will decrease the binding affinity, so called, of the molecule to the protein. That will make those bacteria resistant to your antibiotic, right? Then, if you just continue exposing that culture to your antibiotic, those antibiotic resistant bacteria will take over the entire population. And then you'll have an entire population of bacteria that are resistant to your antibiotic. That idea has happened across literally every single clinical antibiotic we've ever implemented across a ton of different pathogens, right? Okay, so if that's resistance, right? Then resistance as defined as the phenomenon through which bacterial cells do not succumb to
Mhm.
antibiotics that they used to once succumb to. That happens with phage too. It just so happens that that frequency is much, much higher typically for phage, right? It's, so far as I understand, and again, I'm kind of reaching the limits of my knowledge here, it's quote unquote easier for bacteria to become resistant to phage infection, right? That's one issue. Two, oftentimes the phage bacterial interaction is so specific, right? That, it might be to the point where it's like even different members of the same species have differential sensitivity to some phage. So you have to think clinically, if you want to use phage to treat a patient, you have to have a really, really, really good idea of specifically what bacterium is causing their infection before you can use phage as a viable therapy, right? So what happens when phage is clinically implemented is you don't have a single phage, you have something called a phage cocktail, which is like a bunch of phages that all kind of recognize different things, all pooled together, and then that's given to the patient, right? But conventionally, in most clinical settings, like if you come into a hospital and you have a really bad bacterial infection, you're gonna be given, what's called a broad spectrum antibiotic. This is a antibiotic that will kill any bacterium because physicians don't know what you have right away, right?
Mhm.
And they don't wanna waste valuable time trying to figure out what it is before they start treating you, right? So, yeah, like, phage is super cool, and I'm sure there's going to be clinical utility, like more widespread clinical utility as soon as we sort out some of these issues, like the frequency of resistance issue and like the specificity and like even things like infection diagnosis, you know, as soon as we have rapid, inexpensive, like bedside diagnostic technologies that are like globally deployed, this will make phage therapy a lot more viable, right? Because we'll know really quickly what you have and we can pick the right phage. You know what I mean?
Yep. It kind of brings up another thing, which is a little bit interesting as a meta point, right? Like in modern medicine, we isolate things and simplify in some ways and try to explain things based on like mechanisms of action and so on. But in nature, you see a lot of random variation, right? Like when your immune system reacts to something, right? Like it doesn't come up with say one antibody, right? Like it comes up with millions of different variations. Some of them stick, some of them don't, right? And the ones that stick, hopefully, work, right? You get more of them, right? Whereas in medicine, you would be like, well, I'm going to give one drug, and then if it doesn't work, then I'll give another one. If it doesn't work, I'll give another one, right? And it would be interesting, right? If there was an approach that you could say, well, can we I don't know, engineer a whole family of phages that would, go and, evolve on their own, right? And try to kill, all sorts of other bacteria, for example, right? Or design, a whole family of, potential, small molecules, right? Instead of just a single thing that works in a single way.
Yeah. So, I mean, I'm sure folks are doing that with phage. Like, people have to be trying to do this stuff with phage.
Mm.
Um, Here's the issue with antibiotics, right? Like, I love the idea that you propose. I'm going to say why I don't. It might work. I don't know. I'm an idiot. So here's the issue, right? So you know how most medicines, like let's say drugs to treat neuropsychiatric disorders, for example, they're given to patients at doses of milligrams per day, tiny, tiny amounts, right?
Yep.
Antibiotics are given to patients at doses of grams per day, right? Have you seen like a pill of amoxicillin? It's a horse pill. It's this big, right? And it's because you're given so much drug, 1,000 times more than drugs for other conditions.
Mhm.
Um, so by virtue of patients being administered such large like quantities of some antibiotic, like that opens up the opportunity for like a lot of non-specific interactions between that antibiotic and like human stuff,
Yep.
right? So in principle, I love that idea. It's like we don't know like necessarily what the patient has. We have a pill that has a whole bunch of different antibiotics in it. Let's administer that all at once. The issue is you'd be giving someone like a bolus like this, right? To have enough quantity of every bioactive antibiotic such that anyone would elicit an effect. The other thing too is, right, if you have a whole bunch of antibiotics together, all the ones that don't work that well are going to promote the evolution of resistance, right? So we get back to this whole like suboptimal antibiotic therapy drives
Okay.
resistance largely. So, I think that, on paper, I think that idea is like super cool and could potentially work. In practice, there are like current like technological and evolutionary limitations to it. You know what I mean?
Like maybe you would only do it for people that have like sepsis or something like that, where
Yeah.
they have no other choice, right?
And I think
But
that's what like that could be. I actually don't know. Like, but I think in cases where people like do have like blood infections and like they're going septic and stuff, it could be a case. You'll have to fact check me on this. Where physicians just throw like whatever broad spectrum antibiotic they want and just see like, let's see what works. Right. Yeah, I don't know. But you brought up a really interesting point, right? Like you started to touch on it. Um, where it's like nature evolves by accident, right? Like the whole idea of evolution, it's like nature isn't chasing perfection, right? It's chasing good enough for now. That's it. That's what evolution is chasing. And as soon as something isn't good enough for now, you get a little bit of evolution, like again, by accident. There's no like guiding hand here. And then it will be good enough for the new now. And it will be good enough for the new. Like a lot of this stuff we're doing, like with the implementation of ML for, novel antibiotic design, let's say, like it's kind of the same thing, right? It's like we're casting a super wide net across vast chemical space, like orders of magnitude bigger than we could do in a laboratory, letting the good molecules float to the top, bring them into the lab, test them, see what works, see what doesn't, retrain, do the process again, right? So we're like, it's kind of a similar thing through like these iterative active learning loops, right? It's like the good molecules are going to tend to float to the top,
yeah,
and then with subsequent rounds, the better ones will float up and better and better. And then I think the trick is it's like as you're going through, the application of these, whatever, pick your favorite algorithm, I don't care, to identify molecules that do the thing. I actually think one of the most important things that we as humans have to consider is, are we being holistic in how we're picking molecules? Meaning, are we trying to pick molecules that are potently antibacterial, or are we trying to pick molecules that could make good antibiotics? Right? Because there's a really careful, like, there's an important distinction there. An old prof when I was in grad school taught me, like, finding molecules that are antibacterial is really easy, right? Because things that are antibacterial are like bleach and like fire and explosions and like a gun. Like, all of these things are antibacterial, right?
mhm,
Can't treat a patient with any of that, right?
yep,
You can only treat patients with antibiotics, and it's right. These molecules like thread this remarkably sophisticated biological needle to differentiate bacteria from people. Right? So as we're doing all this like fancy ML business, whatever, right? It's really important for us as humans to keep in mind. It's like, what is the end goal we're trying to achieve, and not getting sucked into this trap of I'm trying to kill E. coli. I need to find the most potent molecule ever that can kill E. coli, because there's a non-zero chance that what you're going to find is like a really potent molecule that's anti-life. You know what I mean?
yep, yep. And I mean, going a little bit deeper into that, right? Like, so what kind of technology or kind of a model would be useful for that, right? Like, I mean, surely it's not just, I don't know, some kind of multi-factor optimization, like the statistical optimization that people have been doing for a long time. Right? Like, what kinds of things would be interesting, in order to kind of improve that? Is it some kind of, AlphaFold like, model that understands the structures, or is it some kind of, I don't know, like, large language model, kind of that can pull, research from different areas? What kinds of things are more interesting
Yeah.
for your work?
Yeah. So, I mean, I come at this from an interesting, or I mean, maybe it's not interesting, maybe a boring perspective, right? Because like I'm a wet lab scientist first, right? And I'm using these ML models, and I have to qualify something. When I say I don't actually mean I mean like all the people in my lab. Like I answer emails all day and like beg people for money. That's all I do. I don't actually do very much. It's all so when I say
I'm not a scientist, right?
I get though. Um, but I come at this, I always worry about the data first, right? Like the training data first. So if we go into some drug discovery project, I don't ever ask like, you know, okay, we want to design a molecule to kill staph. I never ask like, okay, what training data exists? Because I don't care. we always think about this as like a data acquisition problem. What does the best training data look like in order to train a model that can generalize appropriately such that it will design molecules that kill staph? So we treat this like purely as a data, or I shouldn't say purely, initially as a data acquisition problem. We go into the lab, gather the best type of training data we can for whatever, and then we ask subsequently, once we have the best possible training data, okay, how do we want to model this? Right? Do we want to treat this as like a language model problem? Like a chemical language model, smiles like next token prediction task. Do we want to treat this as like, like a molecular graph problem using like a graph network, whatever? Or like, is this training data set small enough that we can get away with something as simple as like a random forest or something like old school and easy, right? Um, and then we try a bunch of stuff and just see what works. You know what I mean? Um, yeah, up front, like my philosophy is like, let's keep it as simple as we can for as long as we can and only start to adopt like these really sophisticated models, like when we absolutely have to. You know what I mean?
Mhm.
And I think it's because, again, I'm not the smartest person you're ever gonna meet. You know what I mean? So, like, every layer of complexity we add in, it's like I have a harder time keeping up. So, like, just for my own mental health, if I can keep this simple and still reach the desired outcome, okay, we have a model that can successfully design novel molecules that are active against staph and, like, don't immediately kill a mouse when we put it in the mouse. Like, I'm happy. You know what I mean?
Yep.
Like, you come at this from a different perspective though, right? Because 'Cause you're like a bona fide ML guy, so how do you think about this
No,
stuff?
well, I mean, I wouldn't, I would consider myself more of an engineer than a scientist for sure, or even an ML person, right? But I look at it from the perspective of what kind of tools would be useful here, right? Like, what is the maybe the no-brainer, approach to it, right? And in my mind, yeah, I'm a little bit reductionist as well, right? I think in terms of, well, can we solve one problem first and then solve another problem, then solve another problem, right? So
Yeah.
the way that I would look at it is from the perspective of, how are people doing things now, and can we do that better than any other current approach, and then slowly keep moving from there, right? I think you make an interesting point about complexity, right? And in many ways, um, I think people shy away from complexity when using AI methods, and I'm not sure I agree with that, right? I think it's maybe better to think about what is the right benchmark, what is the right way to measure something, and then even if we don't understand an approach, if the approach works, then
Sure.
that is good, right? Like for the longest time, I think people within AI were um, held back from progress because a lot of folks thought that we had to understand every single thing that is happening inside of a model, right?
Mhm.
You do a random forest, you understand how that works, you understand that you have some features and some are important, some are less important, right? So you can at a you may not be able to go through the entire complexity of a model, right? But you understand, what is happening at every single decision point.
Mhm.
With really, really, really large models like we have right now, it's very hard at an intuitive level to grasp, what is happening if we have a trillion numbers here.
Yeah, yep.
um, and uh, I personally feel okay with that. I think if we somehow were able to get a multi-trillion data point data set that we could use to predict molecules, even if we had zero understanding of what it's actually doing, if we go on and test it and it works, then I think that would be a positive thing.
Yeah.
Whereas I don't know, it may be very, very hard to convince any doctor that that is the right approach.
Well, I think, I think that, like, there's different philosophies here that I'll think they're valid. Like, I think all of them are valid, right? Like, if we're talking about the application of AI in medicine, like clinical medicine, patient-facing medicine, some doc is gonna get some prediction by some model. Like, there's they I don't know, I feel like they need interpretability. It's like, why did this model make this decision in a way that I can understand and also interpret as a physician so I can make the most informed healthcare decision for the patient in front of me, right? Whereas something for, drug design, let's say, I'm kind of in your camp. I actually don't care, what the model learned, like how it got to some endpoint design, let's say, as long as that design works. The people who do care though are, the medicinal chemists who want to optimize this, right? And I've had like many conversations with many, medicinal chemists, way smarter people than I, and they're like, a lot of them, not all of them, they're like, they want to know, why some model made some decision, right? Like, what are the molecular features of this chemical that said, that led the model to, outputting it with a high prediction score, right?
Mhm, mhm.
Um, and so, yeah, I don't know.
Yeah. That's what I mean, that's unfortunately, kind of, trying to grasp for the light switch in the dark, right? At the phrase go. Uh, Maybe just to end because we're already a little bit over an hour, and we want people
Oh yeah, like
actually listen to the podcast and enjoy it, and like be able to do that within a single day, right? And remember, the beginning of the episode by the time to reach the end. Maybe just to end a little bit, like what are you working on right now? What is next for for you, for your lab,
yeah,
for your company. We didn't touch
yeah.
any of that stuff.
So we're just so like on the lab side, we're pretty much all in on molecular design. So we have, a bunch of different algorithms that we're developing and implementing for de novo antibiotic design tasks. And these are across, I'm going to say like nearly every major clinically problematic pathogen in the world right now. Um, and like the whole goal of the lab, if we want to distill away all the complexity, is trying to figure out methods to make drug discovery faster and cheaper. That's it, right? And it is my opinion, whether I'm correct or incorrect. I'm wrong most of the time, right? Like 90% of the time I'm wrong. But I happen to think that the application of these ML models, right, if they're appropriately trained and appropriately deployed, there's a good chance that these will enable a world where drug discovery is faster and cheaper, right? So, drug discovery, it's like $2 billion in 10 years or more,
Mhm.
right? Which is like it's a process defined by failure, right? So the question that you're asking and I'm asking is how fast and cheap can we make this process, right? Like there's no rocket science here. It's like how this is too expensive and too long. Let's make it shorter and cheaper. Um,
Yeah.
and then the company, it's so rad. We have this wicked CEO guy named Jeff Skinner, just like coolest guy ever. He's like a 30-year like Canadian biotech like guru. Um,
Nice.
and our lab is looking at so many molecules at any given time across like a handful of disease areas. Um, that, he gets a look at everything and he kind of has a nose for which molecules for which therapeutic area in which we're working, like have real translational potential, right? And then all of those molecules, after we finish the writing the paper and putting up together whatever we're going to put together for like the academic stuff to keep the lights on to get the grant and whatever, right? That goes over to him. And then the company works as more of like a drug development engine, right? Taking our preclinical like proofs of concept molecules that like novel molecules we discover in the lab that work in like a mouse, for example, and then starting to close that gap between like, hey, we have a molecule that has good proof of concept in a mouse. How do we now march this closer to something that resembles like a clinical medicine, right? Um, and that's what he's interested in, and I'm interested in like just inventing cool stuff. And again, when I say I'm interested in inventing cool stuff, I answer emails all day. So like my students are interested in inventing cool stuff. Um, so that's all I'm interested in, man. Like legitimately, I just what are the mechanisms through which we can make drug discovery fast and cheap? And which is kind of essential for antibiotics, right?
Which I think is one of the most important questions, for humanity as a whole, right? And I'm not being, facetious, right? I think in so many ways, modern society cares about things that are really not as important as, curing diseases and alleviating human suffering, right? And so on and so forth. And, we, as a society spend so much money on things that ultimately are not going to make nearly as much of a difference as actually, living healthier, longer lives, right?
Yeah. I don't know. I'm not like a sociologist. I can't comment on that. Like TikTok is pretty cool though. You know what I
Yeah, don't get me started. I'm not a fan. But I mean, like there were a lot of things actually that I'd love to go deeper on. Maybe I'll text you all those. We'll do a second. I was gonna start,
You'll have to have me back. Well, unless this one nobody listens to this, they're like, "This John guy's dumb, and I don't like him." I could
No, 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 not at all, not at all. I mean, I honestly, I thought this was, incredibly interesting, right? And I mean, I'm, familiar with a little bit of it, right? But I hope, somebody that is just coming at it from the perspective of, like not knowing much about antibiotics and so on, found a whole bunch of interesting stuff and like why this is hard and why is it important and so on.
Yeah. I mean, listen, I hope, like, this is like a remarkable learning opportunity, I hope, right? And people, listen, people listening to podcasts are like driving down the street, like trying to not get into a car accident, right? So it's like if they take away one thing, that's fine by me, I hope it makes their life like 1/1000th of 1% better.
I think that it's you know definitely worthwhile. And yeah, we're at the 1 hour and 10 minutes mark. So
Right.
I'm going to write down the rest of my questions. But this was fantastic. Thank you so much, John.
Ah, man, thank
It's
you.
a pleasure. It was super interesting.
Yeah, tons of fun, dude. Yeah, and if you have more questions, we'll get to it another time.
Yeah, I'll do that and probably reach out around summer. We'll do a second one on like how do we take all these molecules and actually make them into medicine.
Yeah, there you go.
Awesome.
Cool.
Thank you so much.
Thanks, dude.